We are honored to welcome Maria Tsiliakos, partner at the Applied R&D team at Foster and Partners, who will be sharing his insights on the impact of technology and the design of tomorrow. Please.
All good? Okay, good. I would like to invite everyone that's still drinking coffee to please come in the theater. I'm pretty sure you're going to hear some very exciting things today. And I would also like to thank the organizers for the kind invitation. It's very nice being here in Tbilisi for the first time and have a very nice break from British food and enjoy actual good food for once. So, I'm Marius, and I'm a member of the Applied R&D team at Foster & Partners. It's a very small architectural practice in London. Many of the people in this room might know about, but if you don't know about it, we're a global studio for architecture, engineering, and sustainability, founded by Lord Norman Foster around 55 years ago. We have a global presence. We are in 6 continents around the world, and we have 15 global offices. Our office, our headquarters in London, which you can see on the screen, is something like a small university, you would describe it. It's an array of disciplines from architecture, engineering, our own in-house visualization team, and last but not least, our applied R&D team, which I'm part of. Not long ago, even the most ambitious architecture was made with pen, paper, and iterative thinking. Today, generative algorithms, AI, which you've already heard a lot about, evaluate solutions and show us proposals that we haven't seen before. So what is at stake here? Sticking to traditional ways of design bears the risk of missing on a more sustainable, more enhanced future for our architecture. Enhancing technology means that we can produce designs that are not only beautiful, but also quantifiably better than the ones that we were producing before. So quantifiably better both for the communities or for the contextual environment of which they're placed in. So as architects, we're kind of, I think we're in a point where somewhere around there, we have a choice. Either watch this evolution, revolution, whatever you want to call it, from the sidelines, or we can ride the wave of this technological evolution and go along with it. So that's what is the Applied R&D team for Foster & Partners. We're a group dedicated to cutting-edge innovation and research. Our backgrounds, we are currently 34 people. Our backgrounds are ranging from architecture, engineering, software development, data science, but we have one common denominator between all of us. We all know more or less how to write code and build software. And we do have a wide range of expertise and various domains of expertise, from complex geometry, which used to be our bread and butter, to IoT smart buildings and AI, which we're going to talk about today further down the line. So I'm not sure how many of you in here have seen this documentary about Lord Norman Foster and our practice, but this documentary, the title of the documentary, there's a punchline for that, is "How much does your building weigh, Mr. Foster?" This was a question posed by Buckminster Fuller to Lord Norman Foster when he first saw the Sainsbury Center for the Visual Arts, and Lord Norman didn't have an answer immediately, but did Buckminster Fuller really need to know the way of the building? So Lord Norman understood the question as something that highlighted the need for design that used materials efficiently and sustainably. So the question at hand was about the performance of the building, how the building performed, and not how much the building actually weighs. For that reason, today I'm going to focus only on the performance-driven design aspect of or domain of our team. Traditional design workflows often involve multiple stakeholders. You all know you work in practices here, and there can be very tedious and have delayed feedback loops. It makes it harder for designers to build intuitive workflows and assess live how these designs perform, and consequently how these designs are actually looking. Simulation is the easiest way to evaluate a building's performance. And as a historical fact, funnily enough, the form of the Swiss Re was found by wind analysis. In this study, in 2007, which is a building in Glasgow, the OVO, we were trying to evaluate how much of this blue space of the arena each one of the seats in the arena could actually see. So this is something that we is very traditional analysis for us called view analysis. Back in 2007, if a designer were to do this manually, it will take him for one option, let's say of the ball, of the city ball, to a whole day to, let's say, render a view from its seat. This led to the development of our ray tracing analysis tool, Cyclops. Cyclops began in 2007 with 24 views per minute. Now, today, it can run 4 million views per minute. And to put this into context, if the same designer was actually trying to run this analysis with our tool today, he will have to do 160,000 options in one day, which you understand it's impossible almost. So Cyclops allows us to run ray tracing analysis at city scale, so we can evaluate views from buildings. So what do they see? How does performance or radiation analysis is affecting what's happening inside the floor plate? And this is happening live as our designers are actually creating them. A couple of years later, again, in a stadium, 18 years in specific, we use the same analysis for the evaluation of the ball of the new Old Trafford Stadium district. But this time, it's much, much faster. So going back to the same designer, now they can perform all these 160,000 options, evaluating the ball, in only 1 hour, right? It's very difficult to navigate these 160,000 solutions, so we also provide our designers with an intuitive way of going through the various parameters that this control and deciding which ones are the ones that they want to go through, and then consequently they have the form to choose from. In another example, we utilized again the capabilities of Cyclops in the Ellison Institute of Technology in Oxford, which is currently under construction. For this project, our team primarily worked on the geodesic dome, but we wanted to protect it from radiation. We wanted to create a comfortable example, so we iterated through many geometries that actually shade the dome. The analysis can be performed by any designer in our practice real time as they're working in the design software that they are comfortable with being Rhino, being Revit, etc. In other occasions, Cyclops can be used as form-finding tools, where you have a very broad, let's say, space, and then you run analysis from mid-space, and then you identify which are the best parts of the space to actually put a building, how your building performs in these spaces, right? So it helps us make decisions very fast and very early in the design process, so we don't have costly implications afterwards. And I think now it's a little bit of a shameless self-promotion, but I assure you we're not making any money out of this. So 6 months ago, we publicly released Cyclops to the public, and this is in line with our commitment as a practice to sustainability. So any one of you, if you're well-versed with Rhino or Grasshopper, you can download Cyclops for free and use it to run the analysis on your own. In the same spirit, we have our own carbon calculator tool, which assesses the carbon footprint, the carbon impact that each of our designs have, but on the level of concept. So when we decide how to build the volume, we know how is it going to perform. We don't go back to or down the line of detailed design and say, oh, actually, this is very expensive. This is very carbon intense. But what about if you have to evaluate entire cities? Hydra is our distributed computing engine. And I think it's better if I display what it does with an example. This is Guanmi Hub, a project under development in China. It's 2.4 million square meters, the size of it. In this case, we want to create a master plan what is well connected. It has adequate sunlight on all aspects of it. It has views towards the hills in the middle, but at the same time, it's spot on the area that the client has specified. Just imagine this. With Hydra, we can produce programmatically, so automatically, 10,000 of solutions that are at the same time analyzed in terms of performance, and that's overnight. So the next day, we have a series again of indicators of how each one of these solutions perform. Is this the best solution? Is there one best solution? Not really. Our designers are having the opportunity to choose from these solutions and start building their architecture from it. But it wouldn't be architecture without geometry and form, right? This is what it's all about. This was supposed to be the New York, Mexico airport. And in terms of complexity and weight, it's, I would say, thousands of times more complex than Sainsbury's Center that Buckminster Fuller was asking about. So in this case, you have to resort to some of optimizations that give you results very fast and very analytically. So you don't have to always resort to AI. So you have to go to the mathematical definitions of these forms. And then you can use other approaches, as for-driven approaches, for instance, to relax this form, something like Gaudi was doing in the previously in the early century with inverse catenaries. But why does this matter? Believe it or not, most of the panels in this huge airport are roughly the same. This means that they can be easily fabricated, they can be easily transported and assembled, and at the end of the day, it's making the construction cheaper, which makes the construction feasible. You have to be able to construct your design as you designed it. A similar example is the Al Saad Plaza Towers in Qatar. In this case, the project is, I think, it holds a very special place in my heart because there was no static geometry throughout the entire process. Everything was created by a parametric model. And all the data and the design iterations were stored on our cloud storage, and they're audible. You can retrieve them, you can go back to previous solutions, and they can be exchanged within different disciplines with our in-house messaging service, Hermes. Again, having to work with parametric models gives us the opportunity to embed these optimizations within the parametric models. So we don't have to rationalize the facade after it being created. At the end, what we're trying to achieve here is basically forms that satisfy the client brief, right? So it's at different areas. That's what you're optimizing for. And also fulfill fabrication constraints on how the cladding is being articulated, and also how material is being fabricated when a contractor or a tendering contractor is actually going to build it. But that's not always the case. We're not always part of the discussion early on. So there's some other cases like MOL where the team had already had a design and said, okay, how can we make it cheaper? How can we make it something that the client can actually build? In this case, you have to simplify the process. You have to break down the complex elements. You have to simplify it in very distinct elements. And then improves really the performance of the building with changing it slightly, but in a profound way. So in this case, the neck of the building was the most complicated part. As you understand, it has double curved panels. So overall, we managed to achieve an 85% flat panel solution, whereas it was mostly doubly curved in the beginning. And then the other bit was also defined by single curved panels, which, if people know here, they're much cheaper than doubly curved ones. I think if you're an architect and you're in this audience, you've definitely tried to fit a client's brief into a volume or into a plan. So this is our bread and butter. We utilize force-driven approaches to do the packing of, let's say, towers in this case, or in some other instances, we use mixed integer programming, which is a mathematical optimization method to fit this and to fit it the way that we can actually inform the client about their mixes. And if their mixes, the balance of mixes of in this case, it's residences, it's the right for them and for their return of investment. In other cases, when you just have a single plan, it's a little bit more playful, I would say, that you end up having these for-driven optimizations that all these things are trying to find their way around space. In order to make the right decisions, though, I mean, we do a lot of building and a lot of performance, but we have to visualize it in a way. So COVID actually expedited or accelerated our efforts towards this goal. So we had to learn to work collaboratively in a digital review space. This came to be Glaucon, our immersive experiences app. We have used Glaucon on site for building authority permissions. So you go there with the building authority and you review the building as it would look if it were on site, and also digital mockups. And I think it's like we found that it's very nice to be immersed into these spaces. I think Tim previously showed that you can design through them as well, but collaboration really happens in these environments, and it's a very exciting era, especially after the Vision Pro was released. It completely changed the visual fidelity of these models. We also give our clients the opportunity to have, as they design, a marketing app that enables them to communicate what their intent is to some of their key stakeholders, but also to the end user itself. So it's important to include the end users, the residents of our buildings, the dwellers of our buildings, into the process. Last but not least, the key word of our times, we have been training and working with AI since 2016, I would say. This is one of the first experience we had is we utilized the power of artificial intelligence beyond image making at our team. Surrogate models, which is this is one, they help us like streamline slow analysis, and I think Manuela also talked about it in her presentation. But what is important for us is we want to make all of this analysis available to our low-entry designers, right? We want these tools to be able to be used by people that are designers such as yourselves, and not by us that are specialists. Another very exciting topic about the AI, I think, in my opinion, is knowledge dissemination. So how you spread knowledge across your practice, across your office. We have an experience of 55 years, and this is located in PDF documents and drawings, etc. We have deployed office-wide a system called Ask FNP. So a new member of the practice can actually go into this web app, ask a question about, let's say, what is the best insulation in Tbilisi according to the environmental conditions there, and immediately they get an answer from our design guidelines, and this answer is being rated to them with a level of confidence. So instead of going to some senior person in the team, looking through PDF documents in some old files, they just ask a question to this LLM. So this, you understand, it really streamlines and accelerates the way that we work. The same thing if someone has rendered something, they want to specify some materials for the solutions. How do you do that? Traditionally, you would go into a database, you would find materials, you could contract people. Now they can just ask the system, what is the recommended material for this, let's say, visual effect that I have on my view. And you can see they can select the elements, and then immediately they get back material recommendations from our systems. Instead of analytically computing space planning, we also using machine learning to create automated floor plan creations. And this method that's called graph neural networks, the font is a little bit off, but it's fine, no one reads this anyways. And it's a very important especially for the first stages of design, so you don't really want to plan very detailed something, you just want to have an interpretation of it. We want these models to augment the capabilities of our designers in the practice. We don't want to replace the creativity. I don't think that's no one's goal here today. But we're also very keen on retaining our IP and retaining our creative direction as a practice. So we have deployed internally our AI portal. AI portal is a web app that does all the traditional things that you've seen before that you can get from your Rhino viewport. You can prompt something, you can write a description, and then you get an image back with a rendered result of something that I have there is just a wireline model, for instance. But what I think is the best application of this is that we provide with our designers in an edit mode. So in this case, I was going to show you an example from JP Morgan Chase. This is after the project was created, obviously. But we have here a sketch from one of our designers that is very low resolution. And then we provide this editing mode to our designers. And then they can prompt the system, get back results. But they can start talking back to the system and telling it, OK, that's a very nice image, but now remove all the cars from that. And they do this in the safe environment. What I find very interesting is exactly how we retain our IP, how we retain our creative direction. Manuela also talked about this low-rank adaptation method of training your own system. So basically, we give our designers the capability to drop 5 images of something into our system, and then they can create thousands of solutions that actually look similar to what the images that you prompted with look like. And these are a couple of examples that are inspired by our mobility pavilion in Dubai. And I think the favorite one of mine, even though it's a little bit pixelated there, is a Lego interpretation of the pavilion. So you can allow the systems to imagine whatever you want. So what is next? What can be our learnings from this technological revolution for the design of our cities, for the design of our buildings? I think as architects and as designers, we have a choice. Either watch, as I said, from the sidelines, or use these tools to lead the next meaningful and high-impact architecture. And with that, I would like to thank you very much for your attention, and hopefully I will talk to some of you later.